Hello, everyone. Welcome again to our monthly-ish journal club. It is my pleasure to introduce to you the first speaker of today, Sveva Castello. Sveva is a PhD student at the University of Geneva. Previously, she did her bachelor at the University of Turin in Italy. She complemented that with a master at Uppsala University in Sweden. She's interested in, during her PhD work, she works with large-scale structure, and she specifically focuses on studying a promising new observable, gravitational redshift, which she will be talking about today. And I would also like to draw your attention to her YouTube channel, or the YouTube channel that she organizes with a group. They have a lot of very fun videos about science and about cosmology. So I will be linking the channel in this in this chat and in the Slack channel for the Journal Club. And today she will be presenting her work on modified gravity versus dark sector interactions, settling the dispute through the distortion of time. So Sveva, please feel free to start.
Thanks a lot, Enrico, for this kind introduction and also for the invitation to present my work here. I'm very excited actually about this. So what I'm presenting today is part of my PhD project that relies upon the fundamental question of whether cosmological data is able to distinguish between two scenarios. On one hand, a scenario where we have some modification, some fundamental modification of gravity, and on the other hand, a scenario where we have some interaction between dark matter and dark energy, something that is more at the level of some particle physics interaction. And I think that this question is very relevant also in the context of CosmoVerse that focuses on cosmological tensions, because understanding what our cosmological data can tell us about fundamental models to describe the universe is very important in light of assessing different proposed models to solve cosmological tensions. So this is a little bit one of the motivations to ask ourselves these questions. And so let me start by introducing to you the four protagonists of my talk and of my whole PhD thesis, which are four fields that are employed to describe the universe on very large scales. We have two fields that describe the matter content of the universe. So we have the matter density fluctuation with respect to the mean delta, and then we have the velocity field V. And these two quantities that describe the matter content can then be related to the geometry of space-time, which is described by two gravitational potentials, a spatial component and a time component. Now, as in every good story, my four protagonists have relationships among them, and these relationships are provided by the underlying theory of gravity. So if for a moment we assume the validity of general relativity, and we work within linear perturbation theory, assuming a standard lambda CDM scenario, we can derive these relations. So first of all, in general relativity, in the standard scenario, the two gravitational potentials are equal to each other. We can then derive the Poisson equation, which is a relation between the matter density fluctuation and the gravitational potentials. And it is essentially a way to express the way in which matter clusters by falling into gravitational potentials. We then have the continuity equation, which comes from the stress energy conservation, and it relates the density fluctuation to the velocity. And finally, we have the Euler equation, which encodes the so-called weak equivalence principle, which essentially tells us that any test body, regardless of its composition, falls in the same way inside a gravitational potential. However, what I want to do in my research is not to assume the validity of general relativity, but rather to test these relations directly with cosmological data. And the way in which one can do it is by studying what happens if there are any deviations from these fundamental relations. So if we drop the assumption of general relativity, the first thing that may happen is that the two gravitational potentials are different from each other. And then we may have modifications in the Poisson equation. And by convention, when we write down these modifications, the Poisson equation is written down to relate the density fluctuation, not to the spatial component, but to the time component of the gravitational potential. And in the first part of my talk, I will be very general and agnostic concerning the specific kind of modification that I'm looking at. And so instead of looking at a specific model, I will introduce some phenomenological free functions of scale and redshift that encode any possible deviation from the standard scenario. And in the Poisson equation, this function that encodes the modifications is usually called mu. So this is the standard setup that is usually employed when testing these fundamental relations with observations of large-scale structures. So usually one allows for this freedom in the difference between the two gravitational potentials and for a modification in the Poisson equation. And then one constrains these functions. However, you can notice by looking at my scheme that in reality, the standard setup relies upon a very strong assumption, which is the assumption that dark matter obeys the weak equivalence principle. And while this has been tested to a very large precision for baryonic matter on the scale of the solar system, we have no strong evidence that dark matter obeys this principle on cosmological scales. So the question that I raised in the first study that I did during my PhD, together with my supervisor, Camille Bonvan and Nastasia Grimm, who is a postdoc in our group, is what happens to these standard constraints if dark matter violates the weak equivalence principle. And in the spirit of having this very broad and agnostic approach to modifications, we again introduce some phenomenological free functions. We have two functions here. We have a fifth force that acts on dark matter, which is parameterized by a free function gamma. And then we have a friction term that acts on dark matter, which, depending on the action of the fifth force, may sort of slow down or, let's say, speed up the clustering of dark matter with respect to the standard scenario. So these are the fundamental functions that I look at. Now, how do we constrain these parameters with observations? So as Enrico mentioned, I'm working with large-scale structure observations. And in particular, I'm focusing on spectroscopic galaxy surveys, which are surveys that look at the sky and make a map of galaxies as a function of redshift and angular position. And starting from this map, it is possible to build an observable called the fluctuations in the galaxy number counts. So you count your galaxies as a function of redshift and angular position, and you subtract and divide by the average number of galaxies as a function of redshift. And you build this observable, which is called capital delta. And you can write down an expression for this quantity within linear perturbation theory to build a theoretical model of this. And if you do that, you will notice that there are two dominant components to this observable. There is a density term, which comes from the density of dark matter, which is related to the observed galaxy distribution by bias. And then we have the effect of redshift space distortions, which is a correction that comes from the fact that galaxies have peculiar motions on top of the expansion of the universe. And so when we observe the redshift of these galaxies, we will have an additional correction due to these peculiar velocities. So these are the two dominant terms of this observable. And starting from this theoretical prediction, we can then extract information about this observable with a comparison with data. And the way in which this is done is to construct the two-point statistics of the field. So we can build the so-called two-point correlation function, which is essentially a measure of the probability of finding pairs of galaxies separated by a given distance d. And this function can be extracted from observations and compared with theoretical predictions. And these theoretical predictions can be computed in different models of gravity. And it can be, these predictions, for example, can be written down in terms of the phenomenological modifications that I was showing in my previous slide. So this is the setup for my analysis. So in order to assess the different degeneracies between the phenomenological functions that I was showing before, as a first step in our analysis, we studied the kind of precision that we can expect from already available data on the measurements of these functions. So we took measurements from the Sloan Digital Sky Survey of the growth rate of structure, and we analyzed this data with the objective of assessing what precision we can get from this data on our phenomenological modifications. And we first did that as in the standard analysis, meaning assuming the validity of the weak equivalence principle for dark matter and constraining the modification in the Poisson equation mu. So here I'm showing the constraint on the present value mu0, and you see that we get a very tight error bar, which is the same that the SDSS collaboration has published. But then if we allow for a breaking of the weak equivalence principle for dark matter, so we also introduce our parameters theta and gamma, we see that two things happen. First of all, we are not anymore able to disentangle the parameter mu0 alone, but we can only measure a degenerate combination of mu0 with the parameter gamma 0 that encodes the fifth force. And the constraint on this combined parameter is worsened by a factor 30 due to additionally a very strong degeneracy of this combined parameter with the friction term theta 0. So what this analysis tells us is that when you see this very tight bound on mu0, you have to keep in mind that this is based upon the very strong assumption that dark matter obeys the equivalence principle. As soon as you drop this assumption, then your constraints are completely spoiled. So when we reach this conclusion, we ask ourselves, okay, but is there a way to somehow save these constraints? And the answer is actually yes, because there is what we called our deus ex machina, which is literally like a divinity that comes from the sky and saves our constraints, like in ancient Greek theater plays. And this deus ex machina is the effect of gravitational redshift, which is the effect that I call the distortion of time in the title of my talk. So gravitational redshift is an effect that is a prediction of general relativity that takes place when we have a massive object that creates a distortion of space-time. And this massive object is sitting at the bottom of this gravitational potential. And when it emits photons, then these photons will have to escape from the gravitational potential. And in doing so, they will lose energy, and they will thus have an additional redshift component, which is called gravitational redshift. So we can write down an additional correction, actually together with many others, to our galaxy number counts fluctuations that comes exactly from this gravitational redshift. And you see that the expression for this quantity is related to the time distortion in the metric, to the temporal gravitational potential psi. And that's why I call this the distortion of time. Now, this effect is much smaller than the two other effects that were contributing to the galaxy number count fluctuations, the density and redshift space distortions. So current data, for example, from the Sloan Digital Sky Survey, is not yet able to extract this observable. But upcoming surveys, for example, DAISY, and even more in the future, the Square Kilometer Array phase 2, will be able to observe this effect with a good signal to noise. And the way in which we can extract this gravitational redshift is because this effect, together with other corrections, the so-called relativistic corrections, introduces an anti-symmetry in two-point correlations, in the two-point correlation function. And so we can extract it by cross-correlating two different populations of galaxies and performing a so-called multi-tracing analysis. And why is this effect interesting? Why do we hope that it provides additional information on our parameters? The reason is that, as you can see, this observable provides a direct measurement of the gravitational potential psi, which is the one that enters in the Euler equation in the equivalence principle. So by combining this measurement with a velocity measurement, which is what comes from redshift space distortions, we are able to directly probe the validity of the equivalence principle. And that's why we expect additional information from this observable. So as I mentioned, we don't have yet any detection of the gravitational redshift at the level of the galaxy field. So we can't use data to prove this, but we can perform forecasts for future surveys. And this is what we did. We performed a Fisher forecast for the Square Kilometer Array phase 2. And these are the resulting constraints on the set of parameters, on the set of phenomenological modifications that you see that we can. First of all, we can disentangle them. Now we don't have this strong degeneracy anymore, and we recover tight constraints on each of them individually. So this was the first step in our analysis, where we looked at these phenomenological modifications and studied the degeneracies among them. But we can bring all of this to one step further and ask an even more fundamental question, which is the one that is in the title of my talk. So can we distinguish a scenario where we have gravity modifications, so where we have a modification in the Poisson equation and a difference between the two gravitational potentials? So here we have really something fundamental between the link between the matter content of the universe and the geometry of space-time. Can we distinguish a modification in this relation from a modification that comes from some interaction in the dark sector, so some fifth force that acts on dark matter and breaks the weak equivalence principle for dark matter. So in order to put this question into more concrete terms, in a recent study that we did in collaboration of the group of Levon Pogosyan, is to look at two specific models, two example models that belong to each of these two classes. So for the gravity modification side, we looked at a generalized Brans-Dicke model. It's a modified gravity model where we have some additional scalar field that is coupled in the same way to all cosmic components, so to both dark matter and baryons, with a universal coupling parameter beta 1. And we compare this with a model where we again have an additional scalar field, but the scalar field is only coupled to dark matter with a coupling beta 2. And what we ask ourselves is whether we can distinguish between the presence of a beta 1 and a beta 2 in our cosmological data. And in order to, let's say, numerically assess this question, we have performed forecasts, again, for the Square Kilometer Array phase 2. And we have performed the following analysis. So we wrote a code that computes the observables for each of the two models that I'm considering. And then we use this code to generate some mock data vector that only includes one kind of modification. So for example, suppose that you're in a scenario where you have coupled quintessence, so only a fifth force, no gravity modifications, where you have the coupling beta 2 that is equal to 1, the coupling beta 1 that is equal to 0. So you put one modification, and then we performed a fit allowing for both modifications to be there, meaning we analyze this data vector in a completely agnostic way, pretending that we don't know what modification we have put in, and we allow for a freedom in both the coupling beta 1 and beta 2. And we analyze the data with a Monte Carlo Markov chain analysis with a combination of observables. And here I'm showing the result for the beta 1, beta 2 plane. So these are the marginalized posterior distributions for the parameters. And in particular, in this plot, we have the fiducial model that is indicated by this cross. So this is the fiducial model that we use to generate our mock data vector. And then we analyze this data vector. And first of all, we did this with a standard analysis, meaning without including gravitational redshift. And when we do this, we obtain this very strong degeneracy between the parameters beta 1 and beta 2. We have this elliptic constraint such that we can't disentangle the two parameters. We can't disentangle the two modifications. And actually, if we look analytically at the equations for the growth of cosmological perturbations, we can immediately see the shape of the ellipse from the equations. So we immediately see from these equations that we expect an ellipse of this form, where this quantity xc is related to the fraction of dark matter in your model. But then if we repeat the analysis and we include gravitational redshift, what happens is that we are able to sort of close the ellipse and to isolate the fiducial model that we have put into our data. So this means that the inclusion of gravitational redshift is able to break the degeneracy between the two parameters and tells us that the model that we have put in our mock data vector is coupled quintessence and not a generalized Brans-Dicke. So gravitational redshift is able to distinguish between modified gravity and a fifth force. Of course, this effect actually is quite a bit smaller than the redshift space distortion and the density. So it doesn't have infinite power. And so what we have done is to repeat our analysis for different values of the coupling beta 2 in order to see what is the threshold up to which gravitational redshift can help. Because if the coupling beta 2 becomes too small, then gravitational redshift is not strong enough to be able to distinguish between the two models. So we repeated this analysis by changing the value of beta 2. And we also changed the value of the scalar field mass. So in our analysis, the scalar field mass is a fixed quantity because it's degenerate with the scalar field coupling, so we can't constrain the two at the same time. But we performed the analysis with different values of the mass, and we varied the coupling at the same time to set this threshold. And so we have a numerical threshold that tells us what is sort of the smallest value of the parameters such that a survey like the Square Kilometer Array phase 2 will be able to distinguish between the two modifications. So this was our conclusion. The inclusion of gravitational redshift really provides additional information. And I will just briefly mention before going to my conclusions that we have illustrated this point even in a further setup. So far I've been very generic. First, I worked with these phenomenological modifications, these free functions, and then I sort of cherry-picked two models to compare in order to do this controlled experiment and see where gravitational redshift helps. But we have also illustrated our point in the context of a very broad effective theory approach in order to describe these kind of models where we have an additional scalar fields that gives some gravity modifications and at the same time generates a breaking of the equivalence principle. And this study was based upon the so-called effective theory of interacting dark energy, which is this very broad Lagrangian-based approach where we have some gravity modifications that are described by these alpha parameters, alpha m, alpha b. And these gravity modifications cover all the family of Horndeski theories of gravity. So it's a very broad class. And on top of this, we have a breaking of the equivalence principle. And again, like in the previous case, we wrote our own code that computes the observables within this model. And we have analyzed this mock data vector in an analysis with and without gravitational redshift. And we see that when we include gravitational redshift, we cut out some degenerate directions in the parameter space. So you see in these 2D posterior distributions that we remove with the red contours, some degenerate directions that we had in the blue contours without gravitational redshift. And before concluding, let me just give you some physical intuition for why all of this makes sense. So imagine that you're in a scenario where you have some fundamental gravity modifications. What happens is that in a universe with modified gravity, then on average, the gravitational potentials might be deeper than in general relativity, which means that then if you look at the clustering of galaxies, then the clustering of galaxies can be made more efficient because the potentials are made deeper. But in our scenario where you have a dark fifth force, then you have that the depth of the gravitational potentials is exactly like in general relativity. But you could still have the same enhancement of the growth of the clustering of galaxies because of some interaction in the dark sector that can make the clustering of galaxies more efficient. So if you only look at observations of the clustering of galaxies, which is what is probed by standard redshift space distortion analysis, you're not able to tell the two scenarios apart. In order to tell the two scenarios apart, what we do is that we look at something that concerns photons. We look at gravitational redshift, which tells us about how photons redshift by escaping the gravitational potentials. And this gives a measure of the depth of the gravitational potentials in the two scenarios. And so it allows us to distinguish between the two cases. So let me conclude with my take-home message. Gravitational redshift can break the degeneracy between modified gravity and a dark fifth force. And it is a fundamental observable that we should include in our cosmological analysis to be confident that we are really interpreting our data in the correct way. And this is in particular important when we are trying to assess the capability of different models, for example, to solve cosmological tensions. So I leave you with a small advertisement, and I thank you for your attention.
Well, thank you, Sveva, very much. First of all, let me tell you, very good work. I really like your presentation. And so if anyone has any question, please feel free to go. I have a few, so if nobody asks, I'm gonna dig in. Okay, well, since nobody is asking anything yet, I was wondering if I could actually ask you something. So could you just elaborate a little more on the multi-tracing analysis that you mentioned? I think it was kind of halfway through the presentation. I'm just not sure I understood the point.
Absolutely. I think I have some additional slide on this, actually. Yes. So in order to extract gravitational redshift in your two-point correlation function, what you have to keep in mind is that gravitational redshift, actually together with other relativistic contributions to the fluctuations in the galaxy number counts, they will break sort of the symmetry of the correlations. So if you only include the standard terms, density plus redshift space distortions, then your two-point correlations will be exactly symmetric under the exchange of the galaxy pairs that you're considering. So suppose that you correlate a galaxy here and a galaxy here, they are identical to each other. If you swap them, you will get the same thing. And if you expand your two-point correlation into multiples of Legendre polynomials, then what happens is that you will only have even terms. Then if you include gravitational redshift together with other relativistic corrections, then what happens is that this function is not symmetric anymore, but it gets an anti-symmetric contribution. Which,
what do you mean by other relativistic corrections?
So if you want to write down the full, let me see, expression for, wait, let me go back. So the full expression for your galaxy number count calculations includes some standard terms. And then if you include gravitational redshift, and then usually when you do that, you also include other velocity corrections. So this is what I call, let's say, cumulatively relativistic corrections, the thing in yellow and in purple. Then if you include the yellow and the purple terms, then, and you consider cross correlations of these with the standard terms, then your 2-point correlation function is not symmetric anymore, but it will acquire a dipolar modulation, a dipole term in your expansion in Legendre polynomials, which is the term that I was showing here. And since this is an anti-symmetric contribution that comes with the difference of the biases of the points that you consider in front, then if you consider points that have the same bias, you will not be able to extract it. You need to correlate points that have different bias. And so that's why we consider different galaxy populations, for example, a bright and a faint population, because they have different biases and they allow you to extract this dipole term. That is what contains the contribution of gravitational redshift.
So therefore, multi-tracing. Okay.
Yeah, so multi-tracing analysis.
Yeah.